Good morning, students. Now I am going to start, and today is the last lecture in the system of particles and rotational motion. And with this, our chapter will be complete. And then on Monday onwards, or if we will start the next chapter. Okay. Is my voice clear, students? Peer group leaders request other classmates to come into the class. Okay. You request your classmates to come and join in the class immediately. And going to start now. Okay, thank you. And now, okay, our topic is the system of particles and rotational motion. In the last class, we discussed the few things. Its continuation, its continuation. I am going to explain now. Right? There is a one topic is pending, and that is the last topic I will explain. There is a law of conservation of angular momentum. Okay, law of conservation of angular momentum. This is our topic. Very important for the 3 months. Okay, very important for the 3 months. This is the last topic. Law of conservation of angular momentum. What is the law of conservation of angular momentum? What is the law of conservation of angular momentum? We know law of conservation of linear momentum, right? What is the law of conservation of momentum? That when net external force is zero, the total momentum of system is remains constant. This is a conservation of momentum. In laws of motion chapter we discussed. Here conservation of angular momentum means angular momentum will be constant. Okay, the angular momentum of a system, angular momentum of a system is remains constant when net external torque on it is zero. When net external torque on it is zero. Right? This is the statement of the law of conservation of angular momentum. What we are telling it here, when external torque is zero, torque is denoted with the tau. If the torque is a rotating force, if it is zero, then angular momentum is constant. Angular momentum is a capital L. It will be remains constant. This is the statement. Okay, let us go for its proof. Okay, and that proof is just simple. I will tell. It's a proof. We know that relation between the torque and angular momentum. Do you know relation between the torque and angular momentum? We know relation between tau and angular momentum, right? Then what you know, tau is equal to we know as dl by dt. It is exactly similar to the Newton's second law in the straight line motion. That is F is equal to dp by dt. Here F is replaced with the tau and P is replaced with the L. If external torque is 0, what we can take? We take this tau as 0, torque as 0, we will prove Li is constant. You substitute in this in above equation, then you will get 0 is equal to dl by dt we will get. Then from that we will get as dl by dt is also 0. Is it correct? If you will get any doubt while teaching, okay, you test you write in the chart box. Okay, and from this dl is the change in angular momentum is 0. Change in angular momentum, rate of change of angular momentum is 0, means there is no when angular momentum change will be 0, change of angular momentum is 0. When change of angular momentum is 0, if angular momentum is constant, then automatically its change will be 0. Okay, because here dl by dt is the rate of change of angular momentum, means with respect to time how angular momentum is changing, change in angular momentum by time. To follow the arrow mark and where it is explaining. Okay, change in angular momentum by time is 0, that means angular momentum is remains constant. And this is the proof of the law of conservation of angular. It was very simple. Tau equal to L by dt, we know. In the tau you write 0. Okay, we are taking the tau as 0. 0 d equal to L by dt. Then dl by dt equal 0. Indirectly L is constant. Here L is constant means we know formula for L. Do you know the formula for angular momentum in terms of moment of inertia and angular velocity? Any student, anyone can write uh, relation between the torque and moment of inertia, angular velocity. Relation between the tau I omega. Can anyone tell? Or no, 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 not tau and I omega. I want to ask the relation between the L I omega. L angular momentum formula in terms of I and omega. Anyone knows angular momentum formula in terms of I and omega? Yes, you know that one. Ask all the students to join in the class. So many students not came till now. And L is equal to we know as I omega. Do you know this? Then we write as I omega is constant. Is it correct? I omega is constant. From this, because L is equal to I omega, just like P equal to mv only. Linear momentum formula mass into velocity, but angular momentum formula instead of mass moment of inertia, instead of velocity angular velocity you will get. L is equal to I omega, you will get I omega is equal to constant. This we can write as omega is equal to uh, we can write as omega is equal to, what do you write? Tell me. Omega is equal to constant by I we write. Is it right? From this we write as omega inversely proportional to I. Is it right? That means if any due to any reason, if moment of inertia decreases, okay, if moment of inertia decreases, to conserve the angular momentum, okay, to make Li is constant, to maintain Li is constant, I omega should be constant. I omega constant means omega is equal to constant by I, omega inversely proportional to I. If I decreases, what happens omega? Whether omega increases or decreases? Answer students. If I decreases, tell me whether omega decreases or increases from above equation. Answer in the chat box. Do it fast. If you answer, I will read your name. Who is answered? Students, answer. बेबी मातो कहाँ है? Alok increases, right? Any other person increases or decreases? If moment of inertia due to any reason, if it is decreases, then what happens to angular velocity? Yes, automatically increases. Next, if moment of inertia increases, what happens to angular velocity? Angular velocity decreases, right? And from above equation, okay, this we can write here I omega is constant. Okay, and this is considered as equation 1. From equation 1 we write like this also, that is first one we can consider as I1 omega 1, second time we can consider as I2 omega 2, then we will get I1 omega 1 is equal to I2 omega 2, right? Okay. Can anyone give the relation between the angular velocity and the time period? Student, write in the test chat box. You take the screenshot. I am going to take this to right side, left side. Right. Next continuation. If you have the doubts, you can ask anything in the chat box. Okay. Try to learn, and not only writing work also not submitted. Only 7 8 members submitted the notes. The remaining members not writing the notes, not learning anything. Okay, writing is only not important. Writing, learning, okay, understanding, and everything is important. And whatever the work that you are doing at present, and your future will be depends upon this. If you will enjoy now, then your future will be different, will be there. This is the time to do the hard work. This is the 11 12 class. It is the most important in the life. Okay, and the whole life depends upon this 11th and 12th class. If you will read properly, if you will get medical seat, then you will become doctor. If you will seat IIT, if you will get IIT seat after reading in the 11th and 12th, then you will join in the IITs, right? And you will get the good job in the famous companies, right? Like Google or some other famous companies, right? And multinational companies, MNC companies, you can join and you can earn 20 lakhs package per annum, 10 lakhs package per annum, like that. Okay, you can enjoy your life. And if you not read properly, simply if you pass the 12th class, you can join in the degree. In degree you will not get, after the degree, normal degree, BSc degree, you cannot get even a 10,000 job also. It's also difficult, right? Based on the present situation and present working, and your future will be designed. That's why I am uh, telling to you that you must do the hard work in this period. Okay, right. We will continue and we will discuss some applications. Applications of law of conservation of angular momentum. Applications of law of conservation of angular momentum. Applications of law of conservation of angular momentum. Okay, let us discuss. The first application is that ballad dancer. Do you know ballad dancer? Dancer. Okay, ballad dancer can decrease or increase her angular velocity, her angular velocity by stretching or folding hands and legs. Okay, you see here, this is an example for this. And first, I will give one example that one chair is there. This is a rotatable chair. Okay, this can be rotate. Above this chair, you are sitting. Okay, you are sitting above the chair, and somebody is what we are doing it here. So one of your friend make you to rotate. Then while rotating with some speed, what you have to do it here. For example, it is taking 20 revolutions per minute. It is taking now at present. Now what you have to do, what you are doing, this is a rotating on rotating chair. You are sitting on the rotating chair, you are sitting, and one of your friend rotates you that chair, and the chair is rotating. Now what happens? Suddenly you stretched your hands. When you stretched your hands, at that moment you observe the decrease in angular velocity, slowly rotating. And again what you did, you folded your hands. Then again you observed that chair is rotating with high speed. That means just one time, firstly your friend rotated and he left it, and then it is rotating with 20 revolutions per minute. And then what you did it here, now you stretched your hands. Okay, and when you stretch your hands, at that moment you observe that your angular velocity is decreased. You are taking only 10 revolutions, 10 rotations in the per minute, while in the beginning you took the 20 rotations per minute, but now you are taking only 10 rotations per minute. What is the reason why the angular velocity decreased? Can anyone explain? Type in the test box. Write in the test. Write in the chat box. Write in the chat box. Can anyone explain what is the reason? Why angular velocity is decreasing at here? Why angular velocity of the chair is, and the person who is sitting on the rotating chair is decreasing when he stretches his hands? Can anyone explain? No one. Right. Myself, I will explain why the angular velocity is decreasing. Then here what happens? Do you know the moment of inertia formula? Moment of inertia formula is m1 r1 square plus m2 r2 square and so on mn rn square. For example, this is a axis of the rotation. This is axis of rotation, and this object is rotating. This object has the masses m1, m2, and so on mn, and their perpendicular distances are r1, r2, and so on rn, and they are rotating like this. And now what we are doing it here, m1, m2, and so on mn are the mass of the particle, r1 and r2 and so on rn are the distance of the particles. And then moment of inertia formula we can write like this. For example, when the person is rotating, this is the axis of the rotation, right? This is the axis of rotation. About this axis he is rotating. When he stretches his hands, then in the hands particles are there, right? Because your body is made up of particles, the particle distance will be increases from axis of rotation. When you will stretch your hands, then at the moment the particle distance is increased, r is increased, that means moment of inertia is increased. And when moment of inertia is increases, according to law of conservation of angular momentum, then angular momentum should be constant when net external torque is zero. Angular momentum constant means I omega constant. I omega constant means omega inversely proportional to I. Right? When the person who is sitting on rotating chair, right, stretches his hands, at that moment moment of inertia is increasing. When moment of inertia increases, automatically angular velocity decreases. Have you understood this? Write in the chat box if you understood. Yes, you write. And when she fold her hands, when he fold her hands, he or she, whatever it may be, when he fold his hands, then what happening? At that moment he observed that moment of inertia is decreasing. Is it right? When he fold his hands like this, at the moment the distance of the particles from axis decreases. Okay, when distance decreases means I equal to mr square formula. Distance decreases means moment of inertia decreases. When moment of inertia decreases, according to law of conservation of angular momentum should be constant. Then omega is equal to constant by I. When moment of inertia decreases, angular velocity should be increased, right? According to this formula. That means when she stretches her hands, moment of inertia increasing because from axis distance is increasing. When moment of inertia increases, angular velocity decreases. When she fold her hands, okay, then moment of inertia increasing, angular velocity decreasing. Like this, then they can play on the rotating chair, right? And just use what you have to do for this. You have to sit on a table on a rotating chair and make the other friend, okay, ask the other friend to rotate the chair. Then by sitting in the chair, you once you stretch and then fold, stretch and fold, then you will enjoy. This is one type of in some of the parks also this will be available, right, for the game. And at that they will keep some dumbbells also to move the dumbbells away and near to the body. Okay, this is the thing. This is the one of the application of law of conservation of angular momentum. Have you understood what happens when angular velocity moment of inertia increases, angular velocity decreases? When moment of inertia increases, angular velocity decreases. Here, what is ballad dancer? Ballad dancer is also one of the dancer, right? And this dancer also will do, for example, sometimes this dancer want to rotate with a high angular velocity. She want to rotate. Okay, for example, like this, and this is the dancer. Okay, and when the dancer fold her hands like this, for example, she want to rotate with high angular velocity. Omega she want to increase. Okay, omega if she want to increase, then she has to fold her hands. Okay, when she fold her hands, what happens? Distance will be decreases, moment of inertia decreases. Okay, moment of inertia decreases means when she fold her hands, moment of inertia will be less because distance is less. When moment of inertia less, angular velocity will be increases. For example, this dancer, while rotating about her own axis, she is rotating about her own axis. At that moment, if she want to rotate with large angular velocity, then at that moment she has to fold her hands and legs. Basketball. Next, when she stretches her hands and legs, for example, she stretches like this: one hand, two hands she stretched, and one leg she stretched. And at that moment, what happens? Automatically, the speed decreases. Automatically, the speed decreases. Why the speed is decreases? Because when she stretches her hands, then moment of inertia increases. Moment of inertia increases means angular velocity decreases, right? And this is for while folding, right? And this is when she stretch her hands and legs, right? When she stretch, what happens? Angular velocity decreasing. When she fold her hands, angular velocity increasing. That means she is rotating about her own axis. She is rotating about her own axis. During that, right, the ballad dancer can decrease her angular velocity by stretching and increase angular velocity by folding. Ballad dancer can decrease or increase. Okay, ballad dancer can decrease or increase her angular velocity by stretching or folding her hands and by stretching or folding her hands and legs. Have you understood this application? Write in chat box. Write Rahul I proportional to R square. And now you see, Jaya, not understood. Okay, I will take one more example and I will explain. Okay, right. You see, this is the one application. It was very simple. Okay, moment of inertia. According to law of conservation of angular momentum, what happens? According to law of conservation of angular momentum should be constant. I omega should be constant, right? Okay, when if external torque is 0. If tau 0, then angular momentum is constant. Angular momentum constant means, okay, then from this we write as I is omega is inversely proportional to I. Omega inversely proportional to I. When I increases, when increases, if she stretches her hands, then distance increases. This distance is increases here. R is more. When R is more, then I will be more because we know formula for the I, right? Moment of inertia formula is what? I is equal to m1 r1 square plus m2 r2 square and so on mn r1 square. That we write is for many particles if there, right? We can write like this. This we can also write as summation mr square. Okay, mr square. That means if r increases, distance from the axis increases. R is what? R is the distance from axis. If particles distance from axis increases, okay, then at that moment when she stretches her hands, particle distance increases. R increases. R increases means I increases. I increases means omega decreases, right? Okay. Next one is one more application I will tell. That is one diver. Okay. And just like this, for example, this is a diver springboard. Okay. It's a swimming pool. They want to jump into the water. Okay. By the from the diving board. This is a diving board. It has a spring and this is the water, for example, and when one person is trying to take the dive like this, at that moment he will follow this path and he will enter into the water. While entering into the water, he will stretch his hands and legs again like this, and in the middle what he did, you know what he will do, he will fold his hands and legs near to his body. Then at that moment what happens? Why he will fold his hands and legs near to his body? When he fold his hands and legs in the middle of the air, in the air he will fold. Okay, and then what happens, when he jumps onto the diving board, this is a diving board, diving springboard, and then what happens in this case? Here initially he stretches his hands and legs, then during that okay, mm, moment of inertia, when he stretches his hands and legs, moment of inertia will be more. When moment of inertia is more, then angular velocity is less. He cannot rotate it here. But after going to the middle of the air, what he will do? He will fold his hands and legs near to his body. At the moment, what happens? He will rotate in the middle of the air. He will rotate in the middle of the air. Why he will rotate in the middle of the air? Because here, uh, when he fold his hands and legs, moment of distance decreases from axis of rotation, and then distance decreases, moment of inertia decreases. When moment of inertia decreases, angular velocity increases. You know that when he fold his hands, right, then angular velocity increases. Angular velocity increases means then he will rotate in the air. He will rotate in the air. Then after that, when he enters into the while entering into the water, again he stretches his hands and legs. Again he will stretch his hands and legs. When he stretches his hands and legs, what happens? At that moment, again moment of inertia increases. Moment of inertia increases means angular velocity decreases. Then while entering into the water, he cannot rotate because angular velocity decreases. This is the case. One more application. Okay, have you understood now? Write in the chat box, students. Write in the chat box. Do it fast. Have you understood? Very important concept. Diver, what he will do? Curls, means rotates. In middle of air because of how he will rotate, how he will curl in the middle of the air. By folding his hands and legs near to body. Then what happens at here? Here moment of inertia decreases, right? And angular velocity omega increases. But while entering into the water, what he will do? Okay, just before hitting the water, what he will do? Just before hitting water, just before hitting the water, what he will do? He stretches hands and legs, hands and legs, so that moment of inertia decreases and angular velocity, sorry, moment of inertia increases, angular velocity decreases. Moment of inertia increases and angular velocity decreases. Have you understood the concept? Student, clear? Completed? Okay. Very good, Jaya and Nandini Alok responded. Anshu Savay and Suraj also, right? Many of their members responded. Thank you to all. And I will continue now. Right. Now, let us go for one problem based on this. Okay. You take the screenshot and note it. Right. Now, one problem I will explain based on this concept. You note it. The question is that very simple question. It is an NCRT exercise question, and what they are asking in that question, and what we have to find out. Very simple. Okay, a child stands on the first. You write the question. A child stands on the. A child stands on at the, not on the. A child stands at the center of turntable. Center of turntable. table, center of turntable with his two arms outer stretched, with two arms outer stretched. If you have the book, you can open if you want. There is a page number 179, 7.13. A child stands at the center of turntable with his two arms outer stretched. The turntable is set. The turntable is set rotating, with angular speed of 40 revolutions per minute. How much is the angular speed? How much is the angular speed of child if he fold his hands back to and thereby reduces moment of inertia, reduces his moment of inertia to 2 by 5 times of 2 by times of the initial value. Very lengthy question, but easy answer. Okay, right. This is our question. This is the first question, A question. The B question also you can write. Show that new kinetic energy of child more than initial kinetic energy. More than initial kinetic energy. This is our question, right? Can anyone give the solution? It was very easy actually. What happening it here? A child is stands on the center of the turntable, right? Child stands on the center of the turntable. Turntable means this is a rotating table. Child stands at the center of the turntable. Child stands at the center of the turntable with his two arms outer stretched. With his two arms outer stretched. The turntable is set rotating with angular speed 40 revolutions per second. Angular speed. Angular speed means what happens actually? Here revolution per minute they give. Angular speed means angular velocity. This one. Angular velocity formula. For example, if it takes n rotations per second. Okay, the angular velocity they gave is 40 revolutions per second. 40 revolutions per minute. Actually, this is not the angular velocity because angular velocity unit should be radian per second. It should be, but here they gave us the revolution. Revolution means write like this: omega is equal to 2 pi for n rotations. 2 pi n we write by time. 2 pi n by t we write. Here this omega we can also write as n is the number of rotations. Okay, 2 pi small n also we can write. Small n is the number of rotations per second. Number of rotations per second. Okay, initially how many revolutions it is taking per minute? For example, we take the number of revolutions per minute. We can take it as not omega. Omega is radian per second. We can take it as n1. Okay, small n1 we can take number 40 revolutions per minute. Initially it is taking. Initially the moment of inertia we can consider as I. Now what happens? These are the initial values. Now the turntable is rotating. It is taking the 40 revolutions in 1 minute, and the moment of inertia of the child who is at the center of the turntable, okay, who is on the turntable. Now what happening at here? Okay, if anybody did the answer, then you write it in the chat box. Answer you can write in the chat box if you have the pen paper. Right? It is based on the law of conservation of angular momentum. Then question is that what she is doing? How much is the angular speed of the child if he fold his hands back? What happening initially? The person is stretching the hands and it is rotating 40 revolutions per minute. It is taking. Now what happening it here finally? Okay, the new value, the new moment of inertia, he folded child folded her hands and legs. At the moment of inertia become 2 by 5 times of initial value. Then what is the new number of revolutions per minute? How many revolutions with what speed it is rotating? Okay, then we know that according to law of conservation of angular momentum, according to law of conservation of angular momentum, what you know according to law of conservation of angular momentum? Can you tell? Angular momentum is constant. I omega is constant. Omega we write as 2 pi by 2 pi n by t. Omega means angular velocity, angular displacement by time. Angular displacement by time. Time I am taking t. Angular displacement. In one rotation, angular displacement is 2 pi. 2 pi is the 360 degree. In n rotations, angular displacement is 2 pi n. Here it is over 2 pi n by t. Here, this capital N by t I am writing as a small n. Number of rotations per second or per minute, whatever it may be. Right here, omega 1 is, here we can write I1 omega 1 is equal, according to law of conservation of angular momentum, we write I1 omega 1 is equal to I2 omega 2, we write I1 into omega 1 we write as 2 pi n1, I2 into omega 2 we write as 2 pi n2. From this 2 pi gets cancelled. Then we will get the formula I1 n1 is equal to I2 n2. You substituting this, you will get answer, right? Very simple. Anybody got answer? I1 is what? I n1 is what? 40. I2 is what? 2 by 5 into I. N2 we have to find out. This I will cancel. Then 2 20s, right? Then N2 is equal, we will get as 5 by 2 into 40. Then what you will get here? 5 20. 2 20s you will get here. 5 20. 100 you will get 100 revolutions per minute. Now it is taking the 100 revolutions per minute, right? Now it is taking 100 revolutions per minute. This is the question. Initial angular velocity they give. What happening if you once read the question? A child stands at the center of the turntable. Okay, his two arms outer stretched, initially outer stretched. The turntable is set to rotating with angular velocity 40 revolutions per minute. How much is the angular speed of the child if he folds his hands back and thereby reduces to reduces moment of inertia to 2 by 5 times of initial value? The question I will explain. Initially, the child is at the center of the turntable. She stretches her hands. At that moment, the initially the turntable is taking the rotations that is 40 revolutions per minute. Initial moment of inertia I. Now what child did? The child folded his hands. At that moment, moment of inertia decreases to 2 by 5 times of initial value. 2 by 5 times of initial value. Now the new number of revolutions per minute is how much? New angular speed is what? That is our question. We find out that one. Okay. Then what about the new kinetic energy? Show that the new kinetic energy is more than the initial kinetic energy. You can find out the initial kinetic energy and final kinetic energy. Both kinetic energies you can find out. We go for the solution continuation. What they are asking it here? Oh, so B question we can see. Okay, kinetic energy formula is what? Rotational kinetic energy. It is rotating. Rotational kinetic energy formula half I omega square. Is it right? Then here initial kinetic energy means Ke1. We write as half I1 omega 1 square. Hmm? Final kinetic energy is what happening? Half I2 omega 2 square. Is it right? Now divide both of them. Okay, KE2 by KE1 you can find out. Final kinetic energy by initial kinetic energy. What you will get here? I2 omega 2 square by I1 omega 1 square, right? Half cancel. I2 is 2 by 5. I. Final kinetic energy. This is final and this is initial. Now 2 by 5 into I. Omega 2 what we can write? Omega 2. Omega 2 is 2 pi n2. Is that right? 2 pi n2 whole square. By I1 is what? I. Omega 1 is what? 2 pi n square. Right. And now we can simplify it. Ke2 by Ke1. We will get is. You simplify it. 2 by 5 into then 2 pi n2 2 pi n1. You know 2 pi n2 2 pi n1 values. This I gets cancelled and 2 pi square also cancelled. I write this as n2 by n1 whole square. Can you know n2 by n1 value? N2 is 100, n1 is what? 40. Okay, then we write here as 2 by 5 into here 2 pi cancel, that's why n2 by n1 only remains. N2 is 100 by n1 40. Then what you will get? Can you simplify it? 2 2 ja 2 5 ja means we will get to 25 by 4, right? This 2 2 ja 5 5 ja. Final answer is what? 2.5. Final kinetic energy is 2.5 times of initial kinetic energy. That means kinetic energy is increased. Is it right? Initial kinetic energy is Ke1, for example, 1 joule. Final kinetic energy is 2.5 into 1 joule. 2.5 joules you will get. Therefore, the final kinetic energy is greater than initial kinetic energy. Right? When the child folds his hands at the moment, moment of inertia decreases and kinetic energy, angular velocity is increases. Have you understood? Right. Look, 100. Now, we will continue. Next one is the comparison of, okay, in the beginning we started the law of conservation of angular momentum, right? And we continued, and based on that one problem we discussed. Now I am going to compare the linear and rotational motion. Okay, comparison of linear and rotational motions. Comparison between linear and rotational motion. We have to compare the both linear and rotational motion. Previously also you know that one at one place we compared. Okay, now again we have to compare, right? Then for the purpose, let us see, let us start the comparison. One side we take the linear motion and the other side we will take the rotational motion. In the linear motion, velocity will be there, right? Some terms I will tell. In the linear motion, oh, velocity formula is what? In the linear motion, velocity formula is what? Velocity we write is Velocity is the rate of change of displacement we write. Displacement by time. Here you will have the angular velocity. What is the angular velocity? Angular velocity is omega. It is equal to angular displacement by time. And acceleration, what you will get? Acceleration A is equal to, here we have the formula dv by dt. Here we say that that is angular acceleration in rotational motion. Angular acceleration formula is alpha denoted with alpha. Its formula is rate of change of angular velocity. In this momentum formula, momentum is the mass into velocity. In this, angular momentum will be there. Angular momentum formula is what? Instead of mass, moment of inertia you will get. Instead of velocity, angular velocity you will get. Force formula in this MA, or you may know that dp by dt. Force formula here, it will become the torque in the rotational motion. Torque formula is I alpha. Instead of mass, I will comes. Instead of acceleration, angular acceleration will comes. dp by dt. Instead of linear momentum, angular momentum will comes. Next one is the power formula in the linear motion. Force into velocity. Power formula in the rotational motion. Tau omega. Power formula in the rotational motion. Force is replaced with the torque. Velocity replaced with the angular velocity. Okay. Next. Okay, let us continue the differences. Comparisons. Oh, last one is what? Fifth one or fourth one? Last point. Fifth one completed. Next, sixth point I am going to explain. Sixth point. Sixth point in the linear motion. Power we got here. Okay, linear impulse. Impulse formula is what? Do you know impulse formula, anyone? This we learned in the last chapter. Okay, impulse is the in the laws of motion you discussed. Force into time, or the change in momentum we write here. Okay, change in momentum. Here angular impulse we have to write here. Angular impulse. What is the angular impulse? In the angular motion, impulse is what? It is the torque into time. Force is replaced with the torque, but time not replaced with any other term. Time is time only in the same. And the rate of change in angular momentum we have to write here. I into omega minus omega naught we write. Next. Equations of motion what? V is equal to u plus at. Equations of motion. Right? S is equal to ut plus half at square. This is sixth one. This is seventh one. This is the eighth one. In this you will get as there is a wrong accounting. You know equations of motion, right? Equations of motion. This totally we can consider as 7. 7 is the equations of motion. Right, Alok? Impulse is the force into time. Now you see equations of motion completed. Next one is we write eighth one as kinetic energy. In the linear motion, kinetic energy is what? In linear motion, kinetic energy is what? Translational kinetic energy. Yes, it is the formula for half mv square we can use. Or otherwise, we can also use p square by 2m. Is that right? Another formula we use is p square by 2m also. P square by 2m we can use. In the rotational motion, kinetic energy formula is what? Rotational kinetic energy. That is the translational kinetic energy here. It is the translational kinetic energy. Rotational kinetic energy formula is what? Half I omega square or L square by 2I. I will give some idea that can rotate, that can used, okay, to convert the terms from linear to rotational motion. Okay, you see here how the terms will be changes. Linear to rotational motion. How the terms will be there. In the left side linear motion, you know all formulas. Just displacement become angular displacement. ds become d theta. Okay, and initial velocity u become initial angular velocity omega. Final velocity v become final angular velocity omega. Acceleration become angular acceleration. Force become torque. Momentum become angular momentum. Okay, and mass become moment of inertia. Right? If these terms, if you remember, then automatically you can able to write all the formulas in the rotational motion. Is it clear, students, till now? Is it clear? Write in the chat box. Students, is it clear? And the next small topic. What one definition I will go, I will close within 2 minutes. Within 2 minutes, I will close. What is the center of gravity? Next topic is the center of gravity means what? Center of gravity. What is the center of gravity? What is the definition of center of gravity? Center of gravity, it is a point. It is a point at which entire weight of body is supposed to be concentrated. Is supposed to be concentrated. The whole weight of body concentrated at one point. Okay, that is called as center of gravity. Center of gravity is a point. Okay, it is a point at which entire weight of body is supposed to be concentrated. In case of geometrical bodies, in case of geometrical and regular bodies, center of gravity and center of mass are coincide. Are coincide. Okay, and center of gravity depends upon depends upon mass and acceleration due to gravity. Acceleration due to gravity. But center of mass is independent of acceleration due to gravity. Center of gravity depends upon the acceleration due to gravity. Okay, for example, if you go for the ring, center of mass is at the center and center of gravity is also at the center, like this. If you go for the sphere, solid sphere and anything, center of gravity and center of mass at the same position. In case of rectangular plate, rectangular lamina, rectangular lamina plate, the center of gravity and center of mass are at the center. The center of mass means what? Center of gravity and center of mass at the point of intersection of diagonals, like this. If the body is regular body, center of gravity and center of mass are coincide. Okay, this is today's lecture, and with this our chapter is completed. Okay, thank you to all. And if you are not attend for any class, then you can go for the paste. In that every lecture will be there in the system of particles and rotation motion. You can revise and make notes and send me, and also try to solve the example problems. Okay, which are present in the book. If you have any doubt, you can ask me. Okay, thank you, and we will close today's lecture. Thank you to all, and bye. If anybody not give the attendance, give the attendance. Do it fast, and I'm noting the attendance at here at this time.